All right. So, but hopefully you got that part about the stretches. So let me go on to the next example. And close that.
Dr. Russell, where did you post these like examples on there?
This is on Blackboard. I just have to unlock it. But this is, you're not going to turn this in, but I'll still unlock it for you so you can go back and look at it.
All right, thank
you. Yep. Let's see. So here's the third spectrum, and we've already eliminated 2 of these. So the third spectrum is going to have to be either, I think I can get this here. Yeah. It's going to be one of these 2 compounds. Now, why wouldn't it be the second compound? What's missing in the NMR?
There's only 3.
Only 3 signals. Okay, I agree with that. But what signals are not there that we can say definitively that it's not this compound? Let's say it was the same number of signals. What signals are not showing up?
The one that's on the ring.
The aromatic protons, right? Remember, those show up anywhere between 6 and 8. And so this, you don't see that here. So you know that this NMR can't correspond to this compound. Plus, this NMR only has 3 signals. And so you can see from that it's this compound right here, right? So could somebody assign them? You should be at the point now where you ought to be able to know why something is a triplet or why it's a quartet or why it's a singlet. So can you assign them?
What are those? Those hydrogens, the ones that are like next to that carbon.
Right here?
Yeah.
Okay.
Wouldn't those be it'd be basically the signal in the middle. Because
the quartet right here?
Yeah, it has 3 neighbors.
Yep. And it's integrating for 2 protons too. Right. Don't forget your integration. That's also a clue. So I agree with that. Okay. So we're going to call these A. All right. What about the singlet? Which one would that correspond to?
The CH3 and oxygen on the left.
This one right here?
Yeah.
Yeah, I agree with that. Why is it a singlet?
Because it doesn't have a neighbor that would coop.
Yeah, so no neighbors that could couple with it. I agree with that. So we'll call that B. And obviously this is a this set of protons right here is going to be your triplet that shows up here. It's not an O, by the way. All right. So this is a fairly simple spectrum. So let's look at the last spectrum. We've already ruled out everything else, so we know it's going to be the last spectrum is going to correspond to this compound right here. All right, so let's go to the last spectrum. And then here again, let me point out this right quick in the infrared. So in the infrared spectrum, you see this weird looking, jagged looking stretch here. That's your alkyl stretch. So your CH2s and CH3s and carbon chains, they all show up in a stretch that looks like this, somewhere between 2,800 and 3,000. And then there's another important stretch here, which is here. Right, that stretch is your carbonyl stretch. All right, so that's your carbonyl stretch. And every every type of carbonyl, whether it's an ester or acid or amide or ketone, aldehyde, they all have stretches in the same area, somewhere between 17 and 1800. All right, let me go to the next example. Let's do that. And then let's see if we can figure out what's what. So this is the so this is the final example on this sheet. And what do you think so which protons are which? Let's see if we can figure that out. So the ones that are furthest downfield, what would those correspond to? And those are
the ones on the ring.
The aromatic protons. That's exactly right. So your aromatic protons here, 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 and here. Right? Those protons are always going to show up somewhere between 6 and 8. And depending on how they're arranged, sometimes you'll have, you know, some equivalents on the ring because the ring can be symmetrical. In this case, we got 3 signals and 4 protons. So one of those sets of protons has to be equivalent. And I think it's these right here. The 2 that are across from one another. Because if you rotate around this bond, right, and rotate in this direction, this proton is going to end up in the same space where this one is. So I believe it's those 2. I could be wrong, but I believe it's those 2 that are showing up or overlapping as equivalent. Right? Or it could be these 2 that are overlapping as equivalent because they're adjacent to nitrogen. But at any rate, we got at least 2 of those protons on that ring are equivalent because under normal circumstances with no symmetry, all of them should give their own signal. But if you notice the integration, right, is not trying to distinguish between them, right? They all just integrate as 4 protons. And we know that they are aromatic. This is your aromatic region of your NMR spectrum. All right, so that's your aromatic region. And then the rest of the protons are on the chain. So let's see if we can figure out which ones are which. Which ones do you think are going to be the furthest downfield?
The ones next to the ring.
Ones that are adjacent to the ring, that's right. Because this is an sp2 carbon, right? And we know that sp2 carbons are more electronegative than sp3 carbons, right? And so that ring does have some de-shielding capability, right? So these 2 right here, if you look on the spectrum, we're gonna label them as A. Look at the signal. It's a triplet, and it has an integration of 2, right? Why is it a triplet again?
2 neighbors.
It has 2 neighbors.
Yeah, it's got 2 neighbors on this carbon right here. Is that right? And then so the signal is going to be a triplet, right? And then if you look at the integration, it integrates for 2 protons. All right, what about the triplet that's furthest upfield? What do you think that is?
The CH3 on the end.
This one, right? Because it also has 2 neighbors here, right? Sorry about that. Got 2 neighbors on this carbon right here. All right, so that's the triplet. We'll call that D. And then you have two multiplets. One of them should be a sextet and one should be a pentet. Is that right? And which one should be which? Like which one would you expect to be a sextet? How many neighbors would a set of protons have to have in order to be split into 6 lines?
5.
5.
All right, so which one of these has 5 neighbors? Is it the blue ones or the red ones?
The red one.
Red ones, right? You got 2 on this carbon, which I don't have shown, but I can draw them in. Give me about 30 minutes to finish drawing. All right, so there's 2 protons here. And then 3 on this side, right? So for this set, N is 5. So of these 2 signals, what do you think? Because they're both going to integrate for the same number of protons. So this one has 1, 2, 3, 4, 5, 6 lines. And the other one has 1, 2, 3, 4, 5 lines. All right, so it would have to be this one. So we're going to call that one C. Any questions about that? That's got to be somebody who doesn't know that I have a job. Any questions about that signal?
No.
All right. And then by default, this becomes D, right? Let me put the letters over here. All right, so we call the aromatics. We didn't number those or label those, but we just label the ones on the chain. So this was A, and then this was B, and that was C, and that was D. Right? So we do know, I think at this point, we can distinguish between the different types of signals, right? Whether it's a triplet or a doublet or singlet or whatever. We should be able to do that. And we should have a little bit of a grasp on the location, the chemical shifts, and why certain protons show up where they show up. All right. Any questions about any of this stuff? It doesn't have to be from this. It can be from anything that we've talked about. So as everybody feels comfortable with NMR. Well, not, well, I don't know how, I don't want to say comfortable, but do you feel like you could solve a spectrum if you had like choices?
Yeah. Oh wait,
Yes.
I have a little question. So like most of the times when we do one of these like spectrum readings,
Mm-hmm.
like the OH kind of doesn't show up sometimes.
Mm-hmm.
Is that like all the time?
It depends on your instrument. The higher the field strength, you know how like we have a 400 megahertz magnet.
Yeah.
If you have a really strong magnet, then that OH proton is going to show up. But if you have a weak magnet, like you got a 200 or a 250 megahertz, and even a 300, it depends on the field strength of your magnet.
Okay.
Yeah, the higher the field strength, the greater the resolution is for your signals.
So should we like count it as
I'm-
a signal
If I
anyway?
give you an example, I'll probably point it out in the example.
Okay.
Yeah.